Hello dear viewers, welcome to TV MathHub. It is great to have you all here. Please kindly consider subscribing to this channel so you can always get notified whenever a new video is uploaded. In our today's session, I will be taking you through a real analysis objective questions and answers. You will be given 30 seconds to think and get the answer. Then after, we shall give you the correct option. We shall first of all look at 35 objective questions, and in our next video we shall also have about 40 objective questions, making about 75 objective questions in total. So you don't need to miss any of our videos. In our first video we shall look at some of the objectives, then in our next video we look at the final part, which is part 2 of our objective questions. So for those that are preparing for real analysis, please, I get you sorted. Make sure you don't miss any of these objective questions. These will help you in your reading and in your preparations for your final examinations. So without wasting time, let us get started. So we start with question number 1. And question number 1 says, so here is question number 1. Please, you have 30 seconds to think and get the answer. So let us look at the answer. The question says, what does it mean a set to be countable? And the answer here is part A. A set is said to be countable if it is finite, or if there exists a one-to-one correspondence, which is called the bijection, between the set and the set of natural numbers. Very important. There must be a bijection or correspondence between the set and the set of natural numbers. So this makes part A as the best choice, or as the answer. It has only finite many elements. That is not basically complete. It is empty set. Still, this is some case for a countable set. There exists a one-to-one correspondence bijection between the set and the set of real numbers. This is completely out. So the one that is complete, it is finite, and there exists a one-to-one correspondence between the set and the set of natural numbers. So that is the correct option, and I hope that is the option you got as well. So let us look at the second question. You have 30 seconds. The question says, which of the following is an example of a countable set? We have looked at the definition of a countable set. We said the set is countable if it is finite, or if there exists a bijection or a one-to-one correspondence between its elements and the set of natural numbers. When you look at this, this is a set of real numbers. There is no bijection or no correspondence between the set of real numbers and the set of natural numbers. 2, let us look at the set of natural numbers. This is true because this corresponds to actually the set of natural numbers. So this is true. And when you look at the set of irrational numbers, the set of irrational numbers, this is actually uncountable. This is uncountable. So there is no correspondence. And when you look at D, the set of all points in a line segment. So the set of all points in a line segment, this is also uncountable. So basically, we shall have our correct option as B. So B will be our answer. So let us look at the next question. So let us look at this question here. They are saying, is the set of integers countable? The answer is yes. The reason is because the set of integers, which can be written as this set here is countably infinite. This set here is countably infinite. And for that case, it means there exists a bijection between this set here and the set of natural numbers. There exists a bijection between this set and the set of natural numbers, which set of natural numbers is 1, 2, 3, and so on. So there is a bijection. We can easily get a function that takes the elements of natural numbers to the set of integers, and that one can easily be obtained. For example, if you define your function f of n as n over 2, if n, for example, is even, if n is even, and you have f of n as negative of n plus 1 divided by 2 for odd, if n is odd. So if n is odd, we can use this definition here. If n is even, we can use this definition here. For example, if n is 1, then we can get a value here. For example, get 1 plus 1 divided by 2, that will be negative 1. So in other words, if you have n here and you have your f of n, if n is 0, this will also be 0. If n is 1, this one will be a negative 1. If n is 2, this will be positive 1. If n is 3, this will be minus 2. If n is 4, this will be 2. So you realize you'll be able to get this set here because you will have a 0, negative 1, 1, negative 2, 2. So you realize you are able to get a function which maps n to z. And for that case, we shall be able to say that this set here is actually countably infinite. And for that case, the set of integers is countable. The set of integers is countable, and that will be answered. So part A is the correct option. So we look at the next question. So let us look at the answer here. Is the set of all rational numbers countable? The set of all rational numbers is countable, and that will be the correct option. So the correct option here is part A. The set of all rational numbers is it. So as we explained in the previous question, it is also possible to get a function which maps the set, which maps elements from the set of natural numbers to the set of rational numbers. So it is also possible to obtain such a function. So it means there is a bijection. There will be a bijection or a correspondence between this set here and the set of natural numbers. And for that case, it means this set here is countable. So we shall look at the next question. So let us look at the answer here, but it should now be clear because they are saying what property makes the set of real numbers uncountable. So the property that makes the set of real numbers uncountable is that it cannot be listed in a one-to-one correspondence with the set of natural numbers. Because we said a set is uncountable if it is infinite and there does not exists a bijection or a one-to-one correspondence between its elements and the elements of the set of natural numbers. So when, as they simply say, it is infinite, this is incorrect because infinity alone does not imply uncountability. Infinity alone does not imply uncountability. So any, because we know that the set of natural numbers itself is actually infinite, but it is countable. So when it is simply infinite, then it does not mean it is not countable. Then it cannot be listed as a one-to-one correspondence. We have seen that one applies because the set of real numbers, you cannot list it as a one-to-one correspondence with the set of natural numbers. Then when they say it includes fractions, this is incorrect because fractions such as rational numbers are countable. So R includes both rational and irrational numbers. So it does not mean if it includes fractions, then it is uncountable because a set of rational numbers itself is including fractions, but it is countable. Then it includes decimals. Likewise, decimals represent reals or represent real numbers, but the issue is cardinality here. So uncountable, they are uncountably many, not their form. So we say that countable sets can have decimal representations too. So having this one here is not enough to conclude about uncountability. So the correct option here will be B. It cannot be listed in a one-to-one correspondence with the set of natural numbers. We look at the next question. So we want to define what real numbers are, and this I hope it should be easier for us. Real numbers are numbers that can be represented on a number line. That is the answer. Numbers that are not complex, not necessarily rational numbers only, numbers without decimals, not necessarily. So real numbers can also be complex because if you are having a real number as 1, 1 have got the imaginary part as 0. So they can also be considered complex because the imaginary part has got the component which is actually a 0i. So this one does not necessarily define what real numbers are. So real numbers are simply numbers that can be represented on the number line. So that would be the correct. Which sets are subsets of real numbers? So natural numbers, they are subsets. Whole numbers, they are subsets. Integers are also subsets. So actually our answer, it means all of the above numbers are actually subsets of real numbers. So all of the above, because the real numbers are include all rational and irrational numbers on the number line. For example, integers, fractions. So to determine if a set is a subset of R, you have to check if every element of the set is also an element of R. So when you look at natural numbers, when you look at whole numbers, when you look at integers, all of these are included in the set of real numbers. So all of the above will be the correct option. what distinguishes rational numbers from irrational numbers? Okay, so looking at this, basically rational numbers are distinguished from irrational numbers precisely by their algebraic form. So they can be written as a quotient of two integers. So rational numbers can be written as a quotient of two integers, p divided by q, provided q is not equal to 0. So, however, these ones here, irrational numbers, cannot be written in this form. They cannot be written as a quotient of two integers. So when we basically look at these options, the option A, this is correct because they are saying rational numbers can be expressed as a quotient of two integers, which is true. So this one is true because this is a defining property for rational numbers. Then when you look at option B, they are saying rational numbers include decimals. This is incorrect because rational numbers and irrational numbers have decimal representations. So this one will be out. Then C, rational numbers are integers only. So basically this is also incorrect because integers are a proper subset of rationals. For example, when you look at 1 divided by 2 is irrational but not an integer. Okay, so rational numbers don't necessarily include integers only. So D, rational numbers exclude fractions. This is incorrect because rational numbers are fractions or they are quotients. So excluding them would contradict the definition. So basically, it makes part A the best choice, and that would be our answer. We look at the next question. So we have basically looked at what rational numbers and irrational numbers are. So this should be easier for us. So which of the following is not a rational number? That is a number which cannot be expressed as a quotient of two integers, p over q, where q is not equal to 0. So basically, this is a rational number. 0.25, this can be expressed as a fraction. This can be expressed as a fraction, negative 7 divided by 1. So this is true, this is true, this is true. So this is not. So which one is not would be B. So here we are looking at the set of natural numbers. Of course, this should be easier for us to notice. The set of natural numbers start from 1, 2, and above. This one is out, this one is out, and this one is out. So part B will be the correct option. We look at the next question. So what does the Archimedean property state? So here, the Archimedean properties are basically fundamental axiom of the set of real numbers, ensuring they behave with respect to the size and basically infinity. So when we are to look at each of these options, they are saying this real numbers are complete. This is not true because this is the completeness axiom. We know for completeness axiom, every non-empty subset which is bounded above has a least upper bound, or every Cauchy sequence converges. So the Archimedean property is about ordering and addition, not limits. So this will be out. Any positive number can be exceeded by adding another positive number to itself sufficient many times. Option B, this is correct because this is a direct paraphrase, because we know for Archimedean property, if you are given x and y, if x and y are positives and in the set of real numbers, then there exists n picked from the set of natural numbers such that when you get n times x, this is greater than y. So basically, we are looking at the size. We are looking at the size. So when we say any positive number can be exceeded by adding another positive number to itself sufficient many times, this will be correct. Then 3, they are saying real numbers can be expressed as decimals. This is completely out. Rational numbers are dense. This is incorrect because density means between any two real numbers, there is a rational number. So basically, this is from the Archimedean property plus ordering, but it is a theorem, not the statement itself. So here, you realize B will be the correct option. So here we need to look at what is a sequence in mathematics. Part A, an ordered list of numbers. B, a set of integers, a type of function, a property of real numbers. So basically, the core definition for a sequence is that a sequences emphasize order or indexing by the set of natural numbers. So distinguishing them from unordered sets. So this allows the analysis of limits, convergence, monotone, for example, other properties like boundedness. So basically, a sequence emphasizes the order, and like a set which is for just any other unordered elements. So let us look at these given options. An ordered list of numbers. This is true because this captures the essence of indexed progression. So when you talk about a set of integers, this is incorrect because sets are unordered and without duplicates. So sequences can allow repeats. For example, when you talk about constant sequences and non-integers. So when you also look at C, a type of function, so partially this is true, but this is incomplete. This is incomplete because not a general type, not any type of function can give you a sequence. So this will be out. As 3, a property of real numbers. This might confuse with axioms. For example, when you talk about the Archimedean or completeness, so when you look at sequences are objects, not properties, basically. So this will be out. So the correct answer here will be option A. So here we need to look at a series. A series is defined as A, they are giving us collection of numbers. Before we come to the options, basically in mathematics, a series is the sum of the terms of a sequence. So formally a sequence or a series, okay, before we come to series, let us first talk about a sequence. So if you have a sequence, an, from n equaling to 1 to infinity, so where this an is from the set of real numbers. So the series, if you have given this sequence, then the series will be looking at the summation of the terms of this sequence. So n equaling to 1 to infinity of an, like equaling to a1 plus a2 plus a3 plus others. So this one here is what we call a series. So a series is basically the sum of the terms of a sequence. So this sequence here has got terms a1, a2, a3, and so forth. So a series is the summation of these terms. So looking at the options, we are given a collection of numbers. So when you look at a collection of numbers, this is incorrect. Actually, it is too broad and vague. So this could describe a set, a multiset, or a sequence, but it ignores the summation aspect. This ignores the summation aspect, so it will be out. The sum of the terms of a sequence, this is actually correct because this is by definition. This is by definition of a sequence. Then C, the limit of a sequence, this is incorrect because a series converges to a limit. But the series itself is the sum, not the limit value. So this will be out. When you look at the function mapping natural numbers to real numbers, when you look at this a function mapping, this is incorrect because this defines a sequence, not the series. This defines a sequence, not the series. So basically, the correct option will be part B. We look at the next question. What is the nth term of the sequence an equaling to 1 over n for n is an element from the set of natural numbers. So we need the nth term of the sequence. So what will be our sequence? So let us first talk about the sequence. If n is 1, what will be a1? A1 will be 1 over 1. So this will be 1. So the first term of the sequence is 1. The second term n is 2. So this will be 1 over 2. The third is 1 over 3. 1 over 4, the first, and this goes, we need the nth term. So the nth term is when n is equal to n actually. So this will be 1 upon n still. So this continues, and of course, when you look at how this one is decreasing, 1 over 2, 1 over 3, so it goes on, it all goes on, but this will be actually decreasing towards, it decreases towards 0. It decreases towards 0. Though 0 will not be part of the set. So the nth term of the sequence, this is out, this is out, this is true, this is out. So the answer will be C. Which of the following sets is uncountable? So we talked about uncountability of sets, where basically we said a set is uncountable if it is infinite and cannot be put into a one-to-one correspondence with the natural numbers. So basically, let us look at each of these options. We talked about the set of integers. This is countable. This is countable. We talked about this. The set of real numbers. This is uncountable because it cannot be put one-to-one correspondence. Even if you pick a subset of this set here, for example, this set here, this is a set that is basically consisting of many decimals from 0 to 1. So this set here is uncountable. And if it is uncountable, since it is a subset of a set of real numbers, also the set of real numbers will not be countable. The set of rational numbers, we talked about this. This is countable. The set of natural numbers, this is trivially, the bijection will be there. So the bijection is actually to itself. So the set of natural numbers countable, this is countable. The only set which is uncountable is set of real numbers in this case. So that will be the correct option. Okay, so B is the answer. So we look at the next question. So we need to talk about the cardinality of the set A. So cardinality is basically about the number of elements in that given set. So for that case, here we realize this is 1, 2, 3, 4. So there are 4 elements. So cardinality of set A will be B, that is 4 elements. And that will be the answer. The subsets of countable sets always countable. That is true. That is true. The subsets of countable sets are always countable. So that is the correct answer. Is the set of finite subsets of natural numbers countable? The option is also true. The set of all finite subsets of natural numbers is countable. So next we look at the next. This should now be very easy for us to answer. We are saying, what are irrational numbers? We talked about irrational numbers and rational numbers. So basically we said irrational numbers are those numbers that cannot be expressed as a quotient of 2 integers. So this should be easy to spot. So that is irrational numbers. We are looking at numbers which cannot be expressed as a fraction, which cannot be expressed as a fraction. This can be expressed as a fraction. This can be expressed as a fraction. This can be expressed as a fraction. This cannot be expressed as a fraction. So following numbers is irrational. Those are numbers which cannot be expressed as a fraction. So that will be C. Okay, so what is the difference between whole numbers and natural numbers? So basically, let us first of all list these sets here. So whole numbers and natural numbers are both subsets of the set of integers, but they differ in whether 0 is included. So this distinction here is standard in elementary number theory, and basically it is important for all of us. So what is the set of natural numbers? The set of natural numbers is the set which starts from 1, 2, 3, 4, and so on. When you talk about the set of whole numbers, so whole numbers actually also start from a 0, 1, a 2, 3, 4, and so on. So these are positive integers. These are positive integers, and these are what we call non-negative integers. Non-negative integers. So here they extend these ones here by including a 0. So here we don't have a 0, but here we have a 0. So here the correct option will be option A. Whole numbers include a 0 while natural numbers don't. So this would be the correct option. Which of the following is not a property of rational numbers? First of all, I hope you understand what rational numbers are. Numbers which can be expressed as a fraction. When we look at this is incorrect. The reason is pi, this pi here is irrational. This pi is irrational. The pi is irrational. And b, they can be written as a fraction. This is very correct because this is the defining property of rational numbers. They include integers. This is true because when you look at integers, all the integers can be expressed as fractions. Because if you have a 5, 5 can be written as 5 over 1. Okay, big 5 can be written. So integers can be written as fractions. They include terminating decimals. This is also correct because many rationals terminate. For example, when you look at 0.25, this can be written as 1 over 4. This is a terminating fraction. Then others repeat, but the set includes terminating one. So this is also true. So which of the following is not? So answer will be A. So we look at the next question. What does it mean for a sequence to converge? What does it mean for a sequence to converge? So basically, we look at the given options. The terms become 0. The terms approach a single finite value as n tends to infinity. And the next one, the terms grow indefinitely. The next one, the terms form a pattern. So let us look at these options here. The terms become 0. When the terms become 0, does it mean a sequence converges? This is incorrect because the limit L can be any finite real number. 0 is a special case. 0 is a special case. So the limit L can be any finite real number. So this is incorrect. Then when we look at B, the terms approach a single value as n tends to infinity. This is very true. This is very true. This is very true. This is actually the formal definition. So for a sequence to converge, it means it should be tending to a given finite value or to a given value. Then 3, the terms grow indefinitely. This is incorrect because this describes divergence to infinity. So this is for divergence, and this is incorrect as well. Then the terms form a pattern. This is incorrect because patterns may diverge. So convergence requires approaching a limit, not just a regularity. So this one here is not basically true. So what does it mean for a sequence to converge? Is that the terms approach a single finite value as n tends to infinity. And that will be the correct option. Which of the following sequences converges? So which of these converges? For convergence, as n tends to infinity, the terms of the sequence should be coming to a given finite value. should be coming to a given finite value. So for that case, let us look at each of these terms. So when you're having an equaling to n, if you're having an equaling to n, so the terms of this sequence will be a1 will be 1, a2 will be 2, a3 will be 3. So they keep on increasing. So actually the terms of this sequence here, a1 equaling to 1, a2 equaling to 2, a3 equaling to 3, keep on increasing, and this will be tending to what? Tending to infinity. This will be tending to infinity. So the terms will be increasing. They cannot come to a given value. When you look at this, the terms will be decreasing. Let us look at a1. a1 will be 1. a1 will be 1. We look at a2. a1 will be 1, 1 over 1. a2 will be 1 over 2. a3 will be 1 over 3. And this goes on, and this goes on. If n is becoming bigger, then this one here will be tending to 0. They cannot exceed 0. So this will be tending to 0. Okay, so we look at this. When you look at this one here, a1 is when n is equal to 1. This will be negative 1 to the power 1, negative 1. a2, positive 1. a3, negative 1. a4, positive 1. So this keeps on oscillating. So no single limit, no single limit here. So this one here does not come to a single limit. This does not come to a single limit. When you look at this, the terms grow faster than linear, because when you look at a1, it will be 1. a2, it will be 2 squared, which is 4. a3 will be 9. So actually these keep on growing to positive infinity. Keep on growing to positive infinity. So which of these will be tending to a single value as n becomes bigger? As n becomes bigger, you realize it is only in this sequence that these sequences will be coming towards a 0, a single value. So part B will be the sequence that converges. So this diverges, this one here diverges, this one here diverges, this one here oscillates between two given values. So no single limit will be reached for this case. So for that case, it means our answer will be part B. So the question says, what is a divergent sequence? So basically a sequence n equaling to 1 to infinity. So where n are the elements from the set of real numbers. This sequence here diverges. If it does not converge. This diverges if it does not converge to a finite limit. If it does not converge to a finite limit. So what does that one tell us? So when we are to define a divergent sequence, we basically look at such a sequence which does not approach a given limit. So let us look at the given options. A sequence whose terms don't approach a finite limit, this is true. A sequence with no terms, this is incorrect, because an empty sequence is ill-defined in standard analysis, and the sequences have infinitely many terms indexed by n. So basically this is not true. A sequence that is not arithmetic, this is incorrect, because arithmetic sequences can converge. For example, if you have an equaling to 1 minus 1 upon n. So arithmetic sequences, for example, a constant, those that have got a constant difference can converge. When you also, or else, when you have n equaling to n, this one also can diverge. So a sequence that is not arithmetic, basically this shouldn't be an issue. Then D, a sequence defined recursively. A sequence defined recursively. So basically this is incorrect because recursive definitions, e.g. if a1 is 1, a n plus 1 is a n plus 1, describe construction, not behavior. So recursive sequences can converge or diverge. So this one will be out. So what is a divergent sequence? Divergent sequence is that sequence whose terms don't approach a finite limit. And that will be the answer. Which of the following conditions is a necessary condition for a series to converge? Okay, so let us look at the given question. Which of the following is a necessary condition for a series to converge? So the terms of the series must approach 0. So a necessary condition is one that must hold if convergence occurs, though it might not be the sufficient condition alone. So when you look at this, the terms approaches 0. So this is same as having the limit when n is tending to infinity of n equaling to 0. This is true. This is the n's term test. So if you are having the series which is converging and then an tends to 0, then it means your series will be converging. Then option B, the series must be infinite. This is incorrect because finite sums or partial series always converge trivially. So infinite is the setup, not a condition for convergence. So basically this will be out. Then option C, the terms must be positive. This is incorrect because alternating series converge with non-positive terms. They converge with non-positive terms. So this is not necessarily true. Then option D, terms must be bounded. Terms must be bounded. This is true, but weaker convergence. This is true, but weaker because convergence implies that an is tending to 0, which implies eventually bounded. But boundedness alone fails because when you look at, for example, summation of -1 to power n, this is bounded but diverges. So when we look at our option, A is the stricter standard necessary condition for convergence of the series, and that will be the correct answer. So let us look at the next question. So the question says, what is the decimal expansion of a rational number? So we're looking at a rational number p divided by q, where p and q are elements of integers and q is not equal to 0, in lowest terms has a decimal expansion. And this decimal expansion is either terminating or eventually repeating. And for that case, this follows from the division algorithm. The remainders in long division are finite. At most, it is, for example, q minus 1 possibilities that you will have. So they either reach 0, that is terminating, or the cycle, that is repeating. So when we are looking at the decimal expansion of a rational number, let us look at these or evaluate each of these options. A, they are saying always non-terminating and non-repeating. This is incorrect because this describes irrationals. Irrationals are non-terminating and non-repeating, but rationals are terminating and repeating. So 2, always terminating. This is actually incorrect because many can repeat. If you have like 1/3, So this one many can repeat, so not always terminating. So you can have like 1 over 3, which is a 0.333 and so on. Then terminating or repeating, this is correct because every rational fits exactly 1. That is either terminating or repeating. So this is true. Which of the following is an example of a terminating decimal? Before we look at options, the terminating decimal is a decimal expansion that ends after a finite number of digits. So for that case, let us look at the given options. Which one ends after a finite number of digits? So this one here terminates, this terminates, so it ends at a given digit, so 0.75 terminates at the hundredth place. So this is equivalent to having 75 divided by 100, which you can reduce as well to its lowest form, because by 25 this will be 3, this will be 4. So it can be written as 3 over 4. Then option B, this one is repeating. This is repeating. So, and it is equivalent to 1 over 3. Pi is irrational. Root 3 is irrational. So the correct option here, when we are talking about terminating decimal, it will be A. This is repeating, this is rational, this is irrational. The union of rational and irrational numbers form which set? So they form the set which is a set of real numbers. The set of real numbers is the union of rational and irrational numbers. So looking at this, which of the following statements is true? We are given irrational numbers are countable. This is false. Irrational numbers are uncountable. These are uncountable. The set of rational numbers, is dense in the set of real numbers. This one here is true. This is true because between any two distinct real numbers, for example, A and B, if A is less than B, these are our real numbers, A, B. So if you have any two real numbers, for example, A less than B, then there exists a rational number Q such that it has a property A is less than Q, which is less than B, such that this is true. So whenever we say that the set of rational numbers is dense in real numbers, it means between any two real numbers that you think about, then you can always get a rational number. So that is what it means. So for that case, it makes this one true. Rational numbers are uncountable. This is false because rational numbers are basically countable. Rational numbers are countable. Irrational numbers are uncountable. Then every real number is rational. This is false. This is false because we know real numbers are actually the union of rational and irrational numbers. So irrationals, when you say if a real number is rational, then and yet real numbers are the union of irrational and rational, then it means also some of irrational numbers will also be rational, which is not true. So this one will also be out. So this makes part B the correct option. So dear everyone, these are so far 30 objective questions for reanalysis. And if you find this video helpful, please don't forget to like, share, and subscribe to this channel. Here is where we shall stop for the first part, and we shall be coming up with the next part, that is part 2 for the MCQs. And basically part 2 will be taking over 45 objective questions because we want to have at least 75 objective questions. So please don't miss the next part. Kindly subscribe so you can easily get updated whenever a new video is uploaded. We meet in our next part, that will be part 2 of our MCQs for real analysis. See you in the next part.